Got it.
Okay, I will give you the
control back now?
control. Yeah.
Okay.
Give me 1 second. Yeah. Yeah, I just give you the control now.
Okay, good. Okay, sorry about that, folks. That was, I really hope everyone can remember to keep their microphones off, because otherwise it causes a problem for us to manually turn it off and it interrupts everything. Okay, my name's Greg Stone. I've already been introduced, and I'm going to talk about the impact of voltage impulses for modern variable speed drives, let's call it that, on motor windings, and as we'll see a little bit later, also generator windings of certain sorts. And I'm not going to be talking about the conventional aging. Of course, that's also going on of the insulation. The focus here is the insulation, and I won't be talking about normal aging, the thermomechanical, mechanical type aging, contamination type aging that can occur. I'm instead going to be focusing on the what happens in as a result of connecting a winding, an insulated winding, to a drive, and the impact on the insulation. This is, I understood it to be a young people's presentation, or young professionals presentation. So I thought, rather than going into some arcane topic on a very focused interest, that I'd try to do a general introduction to this topic. And I apologize for those who are looking for a lot of specific detail and experimental detail and stuff. That's not going to be in this presentation, so you can sign off now if that was your interest. But I'll you know, I think this should be about 50 minutes long, and there will be opportunities, lots of opportunities to ask questions afterwards if we want to get into some of the details. But given the main audience, I thought I'd do a general introduction rather than going into some details. So what we're going to talk about is just why do we use inverters to feed current to stator windings of motors, and sometimes rotor windings of generators, or some types of generators. I'll very briefly review the various types of variable speed drives, but in fact, I'll be focusing on what's called the voltage source pulse width modulated drive, or inverter. Okay, so this is a particular type of inverter that in fact is by far the most common now in most modern applications. And then we're going to talk about the impacts, and we're going to split that into two different kinds. What the IEC, the International Electrotechnical Commission, and its various standards, I'll be referring to them later, called type 1 windings, which tend to be random wound machines, but do not have to be. And the impact on what's called type 2 windings. Those tend to be 4 wound windings, and in all cases so far, use mica as part of the insulation system to resist the partial discharges that might occur. And if we have time, I'm going to go into the standards in a little bit more detail to see how manufacturers of motors and doubly fed induction generators, how they are now required to qualify their insulation systems so that those machines can be used with inverters. Okay, so I don't know who put that on there, but it's there. Towards the end, at the end, there are some references for a lot more reading. Okay, so why do we use variable speed drives? I'm first going to talk about it on motors, and then I'll have another discussion on generators. But basically what we're trying to do with a variable speed drive, and I'm calling it variable speed drive, some people call it variable frequency drive, some people call it inverter fed drive, some people call it inverter fed drive, and they're all used, and there might be some minor differences between all those different type of designations, but if there are, I get confused about it, and it's not important to me. So I'm more generally going to talk about variable speed drives, and this is where we supply a current and a voltage to, in the case of motors, to the stator winding. The squirrel cage induction motor. And the idea here is by varying the frequency of the AC that we supply to that stator winding, we can change the speed of the motor. And if we slow it down, supply with a lower frequency than rated, it turns out that we'll also normally be supplying it with less voltage, and there will be less power consumption. Okay, so that's what we're talking about with variable speed drives. It's where we are able to supply a current of arbitrary frequency, what's called the fundamental frequency, to the squirrel cage induction motor stator winding to allow it to change speed. Okay, and there's a whole bunch of reasons why you do that. The main issue is normally process control. If you have a conveyor belt and you have less material being shuffled along that belt, you need less power, and it maybe needs to go at a slower speed, and it helps the process so you don't have coal or metal rocks or something like that building up where you don't want it to be. And of course, the same thing in refineries or other applications where it turns out that the process itself needs to be adjusted. Think manufacturing paper from pulp and paper mills, where the process itself inherently likes to be sped up or slowed down. And so this helps with process control and output control and those things. So that's basically the primary reason why variable speed drives have been applied in industrial applications. And then, of course, it's really a corollary of that. If we slow down a motor and also reduce the voltage to that motor, we're going to use less power in that motor. It's not going to go into waste heat somewhere. It's going to be actually less energy is going to be supplied to that system, and therefore we can conserve energy or conserve power. Also, many motors where you have very slow speed processes, quite often you have reducing gears, and sometimes you have increasing speed gears. Well, there's a much less need for gears, and gears are mechanical, and we all know mechanical things are less reliable than electronic or electrical things, at least I believe that. But just as important, actually, and why sometimes a variation of a variable speed drive is just there for motor starting, is most of us know that when we start a motor, there's a 5 or 6 times increase in current going to that stator winding. And that as a result of that hugely increased current, there will be a greater heat loss. Remember, the energy is it's going to be proportional to the heat loss. It's going to be proportional to the current squared, and there's going to be less mechanical forces. Mechanical forces also proportional to current squared. So if you can eliminate or slow down that starting process, so it's a gradual wind up of speed, you are going to have less wear and tear on those motors, because you're not going to have that great huge thumping current going into that stator winding when you do a direct online start, which is the old way of used to doing things. And because you don't have that massive current, you're not going to have those mechanical and thermal forces or stresses that would normally be there. Okay, and specifically for squirrel cage induction motor rotors, the rotor winding, when you turn on a motor, the current on the stator, the current can go up maybe 5 times. On a rotor, it'd be like 50 or 100 times. And that creates the principal failure mechanism for rotor windings, as long as that rotor winding in a squirrel cage induction motor rotor was properly made. Okay, so there's lots of reasons why we want to use variable speed drives if they're economic. And nowadays, when I talk to my friends in the manufacturers of motors, they're saying basically 50% of all new industrial motors are connected to drives. Okay, so that's a tremendous increase from from say 20 or 30 years ago, when it was a relatively small percentage wasn't driven by a converter. And of course, some of the most fastest growing applications of variable speed drives and motors is in fact electric vehicles or hybrid vehicles and aviation applications, where all the motors are in modern aircraft and industrial applications, and electric vehicles rather are connected to drives. Okay, but I should just spend a few seconds on inverters for generators, and I'm specifically referring to what's called the doubly fed induction generators, which in fact are very widely used in, it's a type of configuration of generator that's widely used in wind turbines and increasingly by utilities in their pump storage hydrogenerator plants. Okay, and in this case, what happens is you have an insulated winding on the rotor, and instead of you feeding it DC, you feed it AC current. And the whole idea is, in a wind turbine, for example, if the wind speeds up, then of course the rotor is going to spin faster, but we want 60 hertz or 50 hertz electricity to come out of that wind turbine. And it turns out, by the very nature of a doubly fed induction generator, if you have a specific rotational speed, you can convert that to say 60 hertz electricity by changing the fundamental frequency of the current you're feeding the rotor winding. Okay, so that's a doubly fed induction generator, where inverters then are used to provide power or current to the rotor windings. And because this gives us a very nice 50 or 60 hertz output. In the case of permanent magnet generators, what happens with them is all the power from the permanent magnet generator is then, which is of arbitrary speed, okay, and arbitrary frequency, is converted using an inverter or converter, a DC link plus an inverter to provide the 60 or 50 hertz electricity that we need for the grid. Okay, so these are the two primary applications for the variable speed drives, and where the impulses, the voltage impulses from those drives, might lead to premature aging of the electrical insulation on the windings they're connected to. Okay, and this is just a nice picture of an all-electric plane that flew about a year ago or so. Some of you might have seen it on the cover of the Electrical Insulation magazine. It was a plane, an all-electric aircraft made by Beta Technologies in Vermont, where it has 4 lifting motors that you can't really quite see in this picture, plus a pusher motor, as they call it, to drive the aircraft along. And it was kind of a really nice picture because you see all these wind turbines, which are also have inverters in them to feed current to the doubly fed induction generators. Okay, so the types of inverters. There's lots of types, and even a long time ago, when I was still in school, we talked about variable speed drives using load commutated inverters. Typically where you have thyristors or silicon controlled rectifiers, SCRs, whatever you want to call them, to switch DC bus voltages to provide an output current of any desired frequency. Okay, the other type of drive, those LCI inverters were very common in the olden days, less common now, typically being replaced either by current source drives or voltage source drives. The current source drives is popular from some manufacturers, but I gather they tend to still be a little bit more expensive and have a bigger footprint. And so the type of drive that's most common today is what's called the voltage source PWM drive, or pulse width modulated drive. And in fact, that's the one that tends to cause the problems for the winding electrical insulation. And so that's what we're going to be concentrating on here for the rest of this webinar. Okay, so voltage source PWM inverters or drives, what you have, and I'll show you a sketch in a few seconds, but you take, there's a positive DC voltage and a negative DC voltage, and you just use switches, okay, electronic switches. In our case, it's almost always, or in the industrial cases, so far, it's mainly induction, insulated gate bipolar junction transistors, IGBTs or IGBJTs, which then can turn on and off the DC, and by clever arranging of turning on and off either the positive or the negative DC supply, one can then generate, and varying the width of the pulse that you supply, you can generate a nice AC current of any frequency that you want. Okay, now as I said, in most industrial applications and almost till today, we use IGBTs, and in fact IGBTs have been used in PWM drives right up to 13.8 kV, or really 15 kV windings in motors, and although they might be cascaded to create multiple levels, but more and more, especially in the electric vehicle and aircraft applications, they're using what's called wide bandgap switches like silicon carbide, and there's other exotic materials which in fact can switch in much shorter than 30 nanoseconds. In fact, I'm aware of one situation in an electric vehicle application where the rise time of the voltage impulse that can strike that stator winding is as short as 7 nanoseconds. Okay, so and there's reasons why they want to make that rise time shorter. The shorter the rise time, the less heat that will be created. Therefore, the more efficient the drive will become. I'm sure all of you listening to this are very well aware of that when you switch a device, it's not when it's either fully on or fully off that you're really absorbing energy in the actual switching device. It's just when it's in the transition from off state to on, or vice versa. And of course, so the semiconductor industry has been doing everything they can to shorten those rise times, because the shorter that rise time, it turns out the less time that switching device will be heating up, and therefore the less effort we have to make to try and suck all that heat away, so the converter or inverter does not overheat. Okay, and this is why it's become the IGBT and now the wide bandgap switches are becoming more and more popular, because they allow smaller footprints and smaller heat loads for equivalent power output from the inverter. Okay, so in case you're not familiar with it, this is just a sketch I swiped from somewhere where you can see there's a plus DC bus voltage, a minus DC bus voltage, and then there's ground, if you want to think of that, or 0 volts. And you either have switches that switch on and off the negative DC bus voltage, which is happening here, and then switching on and off the positive DC bus voltage here. And then what you can see, if you smooth this out, and especially when you're going into a reactive load like a motor winding, you will then have a nice smooth fundamental frequency of any desired frequency that you want. Okay, so you'd get a current there that would then drive that motor in this case, and you can change that frequency just by changing how you switch on and off the DC bus voltages. So this is what might be called a 3-level, or some people might call it a 2-level inverter, because 1 level, 2-level, 3-level inverter. Typically, this is used for motors and generators that are where the windings are rated less than 690 volts or so, less than 1,000 volts. But then as we got to higher and higher voltage machines, as I said, we have motors out there at 13.2 kV now, and they tend to stack these inverter stages on top of each other or combine them in some way in a transformer, so that there are even more levels. And I'm aware of inverters who've got up to 11 levels. I'm calling this 5 levels. Some people might call it less than that, depending on how they define 0. But this is level 1, level 2, ground, level 3, So that'd be level 3, level 4, level 5. Okay, so you have more levels, and sometimes this actually will help us in terms of the nature of the impulses that strike the winding. Now, if you look at this and you see I've put a little glitch in here, and you see it's not just a simple pulse of arbitrary width here. What it is, you see when it switches, there's a bit of a transit. And if we blow that up or zoom it up in a digital scope, you'll see an image like this. Now, this is an old image I took probably 20, 25, maybe 30 years ago. This is of a 460 volt rated motor that was connected to a Voltage Source PWM drive. The key thing is to note the time domain, okay? So this is 100 nanoseconds per division. So we can easily see that between 10% and 90% of the peak, we have a rise time on the order of just under 100 nanoseconds. So that's the key thing. We get a fast rise time or a short rise time. And those of you who can remember your Fourier transforms, this will translate into frequency components up to a few megahertz. Okay, and this is going to cause us problems a little bit later. Okay, so the origin of the surges are, of course, as we're switching these, turning on and off this DC bus voltage, and those switches have relatively fast rise times. And then we can get transmission line effects, because in most industrial applications, you'll have the inverter in a nice, clean, dry, air-conditioned building, and then you'll connect it to the load by a power cable, and that load will be in a messy, wet, humid, hot, noisy environment, usually in a refinery or a pulp and paper mill or a steel mill, and so you don't want the drive, which is full of electronics, near where that motor has to be. So you use cables. And this is where we get traveling wave effects, okay? And where a pulse or volt, that pulse will travel along the surge impedance or characteristic impedance of that cable, and then it'll hit the characteristic impedance or surge impedance of that motor. And unless they're exactly the same, and they never are, what will happen is there will be a reflection, just like a water wave hitting a brick wall, and then you'll get a reflection back, and that can give rise to up to a 2 times over voltage. So we get transmission line effects, and that can affect the magnitude of the pulse and, as it turns out, the rise time. So what affects the surge magnitude? The length of the power cable. If the cable is really short, it turns out you won't have those transmission line effects. And this is why you see in electric vehicle applications and aircraft applications, they basically bolt the inverter right onto the motor. So there is no cable, and this prevents this doubling of the overvoltage. The other thing is where you do have cables is the ratio of the surge impedance of the cable to the surge impedance of the motor. And those of you who are familiar with your transmission line equations, you can write all that out. It's been around, that knowledge has been around for a long, long, long time. Okay, grounding of the power cable also has an impact because it affects the surge impedance, and therefore the ratio of the surge impedance of the winding to the surge impedance of the cable. And in fact, effectively, most cabling, even for low voltage motors and stuff, is usually shielded in some way for electromagnetic interference reasons. Okay, so this is always something that can affect things, and it makes things worse. Also, there's the fact that there's attenuation. As impulses travel on a cable, there will be an impact on the magnitude of those cables, as the losses in that cable suck away some of that energy. Okay, but there's rise time, and you'll see why rise time is going to be important in a few more minutes. But and usually the shorter the rise time, the more danger it is to the winding. Okay, but assuming you know that already, and I'm sorry if you don't know that, I'll be talking about it in a few seconds. It turns out that if you have a longer cable, the rise time will gradually slow down. And this is basically because of the insulation shield and conductor shield on the cables, which absorb energy, especially at high frequencies, and therefore the high frequency components are more strongly attenuated than the low frequency components. And this effectively lengthens the rise time, and that makes this surge then more benign to the machine. Okay. And of course, insulating material has the best thing in the whole world is if we could go back to paper insulated lead covered cables, because they absorb and attenuate and distort the pulses from the inverter really well. But for some reason, people don't like that anymore. I guess it's that lead thing. Okay. So now I'm going to start looking at what is the impact of these impulses, voltage impulses from the converter on windings. And I'm going to separate it, as I said right in the beginning, into random wound and form wound. It's not really that. It's really should be type 1 and type 2 windings. But let's talk about it in terms of random and form wound windings. Random wound windings, and I'll show you a picture in a second, are usually the lower voltage machines. And you're probably all familiar with it if you have houses and you've taken apart a motor on a furnace or something, or taken apart an alternator in a car. Okay, form wound machines are usually on machines 1,000 volts and above, but where high currents are involved, sometimes they'll be used on low voltage windings too. Okay, and as I said, the impulses from the inverters affect the random and form wound windings differently. So this is a random wound winding. Hopefully you can see the stator core is here. You can see the coils that have been inserted into the slot. Usually there's at least 2 coils per slot, and they've been put in there. And you normally then have round insulated copper wire, what we tend to call magnet wire in North America, and the rest of the world calls winding wire. But it's insulated copper, and where the insulation is a polymer film, one of the common ones being polyamide imide. Okay, and that's that brownish purplish material you see on motor windings and stuff like that. And the big issue here is why we call it random wound is because that conductor from one turn in that coil can be adjacent to any other possible turn in that coil. There's kind of a random placement there. And this is what can sometimes cause us some problems. So here's a diagram from an IEC standard of just, if you look at the cross section of a coil just outside the slot, here is the stator core in this case. Here are the copper conductors. Up here would be the rotor. So I hope you see where I'm looking at here. And what you see here again is the insulated round wires, the magnet wires. Then, as I said before, you tend to have 2 coils in a slot. So this coil might be from phase A, this coil might be from phase B. So we need to have some insulation separating those. And we also have a slot liner in here that would be the make sure those copper conductors don't come in contact with the grounded laminated steel core of the stator winding or rotor winding, whatever it may be. So it turns out we have turn to turn, phase to phase, and phase to ground insulation. So the turn to turn insulation is just that thin magnet wire or insulation on the magnet wire. And the ground insulation separates the copper conductors from the core, and the turn insulation, or rather the phase insulation, separates what coils in one phase from another. That's this piece of paper here, or that strip, and or in the slot. Okay, so this is the general structure of the insulation system. Okay, so I'm now going to create a bit of a story here. And so the overview is when we have those short rise time impulses, they have high frequency components that result in very high voltages between the turns in a coil, in any individual coil in that rotor or stator winding. If there are air spaces then between these turns, you could have partial discharges. And partial discharges, which are small electrical sparks, hopefully should not be occurring, will lead to, but if it is occurring, because we have organic insulation, it's just a polymer film on that magnet wire, that PD will gradually, in fact, fairly quickly, eat a hole or create an electric tree through that insulation, causing it to fail. Once you have a turn-to-turn fault, it turns out you're going to have the magnetic flux from all the other turns in that stator winding feeding flux into that one shorted turn. The current's going to go up, say, 100 times, and all of a sudden you're going to be melting the copper conductors, and which will then melt any insulation between there and ground, and you're going to trip out on a ground fault or an earth fault. Okay, so that's the overview. So I want to take us through each of those steps. So the first thing is, I said there'd be a non-uniform distribution of the voltage across that winding. Well, at 50 or 60 hertz, and this is another just a Y-connected motor stator winding or rotor winding that I'm showing here. This would be phase A, phase B, and phase C terminals. And then we have the neutral at this point, which may or may not be connected directly to ground. And the idea here is we normally then have several coils, each with several or multiple or many turns connected between line end and neutral. Okay, so if we have, say, a 400 volt line to ground voltage, okay, it would turn out that in normal 50 or 60 hertz operation, we'd have an equal voltage across each one of those. In fact, if it's 400 volts applied phase to ground and the phase to ground here, that would mean there's basically 100 volts across each of these four coils, okay? Because it turns out at 60 hertz, they all have the same inductance. Each coil has the same inductance, and they'll have the same inductive impedance, which is given by 2 pi f, the AC frequency, 50 hertz or 60 hertz, and the inductance of that coil, whatever number of millihenries it might be. And of course, when they make the motor, the manufacturer makes sure there's the same number of turns in the coils, and they each have the same inductance, which means there's the same inductive impedance in which case. And if you say we have 4 coils in series, and each coil has, say, maybe 100 turns, well, we're going to have 100 volts across each coil because of its inductive impedance. Remember, current goes through the path of least resistance. And then what will happen is if we have 100 turns in that coil, then there might be then 1 volt between the turns. And it doesn't matter whether you're the line end in the middle of the winding or the neutral end, you're always going to have that 1 volt or 2 volts or 3 volts, but it's in that order of magnitude across the turn insulation. And since that turn insulation is good for way more than a few volts, we have good turn insulation then. The problem is when we hit it connected to a voltage source inverter, because as I showed, you get 100 nanosecond rise time pulses coming out of there. Okay, and if you take the Fourier transform of that, that will correspond to frequencies up to about 3 megahertz, not 50 or 60 hertz, 3 megahertz. So a 500,000 times higher frequency. Okay, now when you put that frequency, instead of putting 50 hertz in here, but put 3 megahertz in here, all of a sudden that inductive impedance becomes megohms, or at least hundreds of kiloohms. And current doesn't like going through hundreds of megohms, or hundreds of kiloohms rather. Okay, so the current doesn't want to just normally travel right through that winding. Instead, it wants to find a less a path with least impedance, and that then means it's going to find the path to ground through the capacitance, because those copper conductors, you saw they were inserted into that slot. There's a lot of capacitance between the copper conductors and the stator core, and typically it might be on the order of nanofarads or so. And if you then put a coil in here and you have the inductance of that coil, and then you have its capacitance, the current doesn't want to go through the inductance, it's going to go through the capacitance. Effectively, after the first coil, this all appears like just a big capacitor, and this is that after the first coil, the coil is dropped, the voltage at this end, at the low side, the farther end from the terminal, is essentially 0 volts. Okay, because of that big capacitive impedance. And there I've talked about the coil, but the same thing happens on each individual turn. There's also capacitance between the turn and ground, although it can get very complicated because the turns might be in fact far from ground. So it's a very complicated, messy circuit. But I think you can understand the basic principle is that capacitance, even on the first turn, might be so high that the current goes through that first turn and immediately is effectively at ground potential. That means instead of having just 1 or 2 volts across the turn insulation, across that, the polymer film on the magnet wire, you're going to have possibly the full voltage. You remember I showed you that voltage earlier. I guess I shouldn't have gone back. I should have mentioned this, but here it is, a 460 volt rated motor, and we've got 2000 volts applied to that machine terminal. Okay, because this is a measurement I did right at the machine terminal. Okay, so what happens is now we've got like full voltage across those turns, and this is where it causes problems then. Okay, so this material I've already said, it's because of the capacitive effects and the fact that current always wants to go through the path of least resistance, which happens to be when you're dealing with 3 megahertz through the capacitance to ground. Then what happens is almost all the voltage is dropped across the first turn of the first coil. Okay, and here are some measurements we did a long time ago where we just used an Agilent or Keysight or whatever they're called today, pulse generator with a variable rise time, and we applied 5 volts to a random wound stator winding, and we found the voltage across the percentage of voltage applied to the that appears across the first coil at 100 nanoseconds is like 75% of that voltage is applied across that first coil. And if we could go in and look at the individual turns, we'd find even after the first turn, there would be a high voltage. Okay, and so this is the problem. Notice this was done a long time ago. I didn't even think to try and go down to 5 or 10 nanoseconds back then. I didn't expect that would ever actually occur. But if you extrapolate that, I think we can probably safely say that almost 100% of the voltage from a wide bandgap switch device like a silicon carbide switch might in fact be across the first turn. Okay, so what's the consequence of this? Well, remembering that cross-sectional image I showed you before, let's take 3 turns, put them side by side. Here is the copper conductor from that magnet wire. Here is the polymer film. It's showing much thicker than it really is for that particular copper conductor. This is the turn insulation. And let's say we have an air gap here, which is not uncommon, or certainly was not uncommon back in the early 90s when problems were first being found. And what happens here is if you get that 1,000, 1,500 volts across a small air gap, given the very thin insulation coating on the magnet wire, you can easily, if you have finite element electric stress model, you can easily see that it gets to very high electric stresses. And in particular, it might get to the 3 kV per millimeter peak voltage that would, if this is air and dry air at 100 kilopascals or 15 psi, would mean that there's a high likelihood that you're going to break down if there's an initiatory electron from somewhere. And so you're going to get that breakdown just in the air gap. And of course, we refer to that as a partial discharge. And that partial discharge will, because this is purely organic material, it just turns out organic materials are very, very susceptible to aging or destruction, molecular bond scissions in the presence of these repeated partial discharges, the electrons that are going to be hitting that material from the partial discharge. Okay. Also be aware of that if you're at lower pressures, okay, because you're at higher altitudes in aircraft things. This is why I'm a little concerned when I get into certain modern jets when I'm flying across continents or between continents. You know, you're at much lower pressure, and therefore there's even a lower breakdown field strength needed to break down that air. Okay, so here's just an example of an industrial motor where there was partial discharges occurring between the turns caused by inverters. And of course, it failed. The turn-to-turn insulation failed. There was a lot of melted copper around there when we did the forensic analysis, and that's a sure sign of shorted turns. And then, but all the soot and stuff is caused by the fact that, of course, operators like, well, it didn't start. Let's try it again. Let's try it again. Let's try it again. And you get a lot of collateral damage that makes forensic investigations a little bit more of a challenge. Okay, so I've dealt with the random well windings, and problems started occurring there. The first reported problem that I'm aware of is a guy, someone who I'd never met in Vancouver, who's a consultant, a guy, Mr. Person. I don't know anything more than that. And he wrote a paper at an IEEE Industry Applications Society conference saying, hey, they're getting failures on 440-volt industrial motors and pulp and paper mills, and it looks like partial discharges when we look at it. Okay, so he was the first one. Since then, there's been a tremendous amount of activity. And in fact, most manufacturers now have solved the issues with drives. If you know, so there are now inverter duty motors that will make sure that they're partial discharge free at their operating voltages and with the expected surges. And we'll talk about that a little bit later. Okay, but a lot of effort happened, mainly because those motors were failing literally within months of being turned on, and certainly within the warranty period of the motors. So the OEMs were highly motivated to try and fix that problem. And I think they largely have by better impregnation methods. Okay, now let's deal with form well windings, which are typically 2 kV and above, but there's a lot, almost all wind turbines also contain form well windings in both their rotor and stator windings. Okay, so these motors are now getting very large for LNG compression applications, and 65 megawatts. I think they're up to 85 megawatts now. The form well windings. The key thing is we still have turn, ground, and turn-to-turn insulation, but there's also a different component, an additional component in these machines, and then I'm hopefully you're part of aware, because I've got to start getting down to the end here pretty quick, and that it's the PD suppression coatings both in the slot and in the M winding, where we use partly conductive tape or paint on the surface of the coil in the slot to prevent PD between the surface of the coil and the stator core, because there's always going to be an air gap there. And when you get to voltages 3 kV and certainly 6 kV and above, you'll initiate PD without those semicon coatings. And then just outside of the slot, we have what's called a silicon carbide stress control coating, or some people call it an ECP, but it's the same thing as the terminations, the high voltage terminations you see on power cables. Okay, and it's a magic material that prevents partial discharges just at the slot exits. Okay, and so here's an image of a coil. So this is a form wound coil. It's completely made or almost completely made outside of the slot and formed into a special shape. It almost always uses rectangular copper wire, magnet wire, and then we have ground insulation, and then we also have the stress control or PD suppression coatings. Okay, here's just another image, again, taken from an IEC standard, okay, where this is the stator core, again, 2 coils in a slot. Here are the copper conductors, the high voltage insulation, and the semicon material just in the slot region to prevent PD. Okay, and there's just an image of a motor. Again, the stator core here, insulating wedges here, and the coils coming out of the slot. And you can see that black semiconductive coating is there to prevent PD in the slot. And there's also this matte silicon carbide coating that stretches out here that linearizes the electric stress in this region. Okay, and it does that through a magical way. It's well understood. Okay, so I talked about for the random well windings that PD seems to be the issue, primarily between the turns, although it could happen between to ground and between phases, but primarily between the turns, because there's quite often air spaces there, and then you get those very high stresses. Well, the same thing can happen on form wound windings. Okay, that if we have air gaps between the turns, instead of the normal 10, 20, or 50 volts between turns, we can have this nonlinear voltage distribution and get a few thousand, up to maybe 1,000 volts or 1,500 volts between turns, which might initiate PD. We also thought that there could be the converter could affect the windings because it would cause additional heating, really due to dielectric losses, and it could cause additional ground wall PD, primarily because of those voltage spikes sitting on top of it. Turned out that didn't seem to be too important, and I'm just going to skip over these in this presentation. But something that did catch us by surprise, or at least it caught me by surprise, is that the PD suppression coatings, those black and those black coatings in the slot and the gray or red coating just outside the slot, they failed very quickly unless they were purposefully designed for inverter applications. Okay, so the turn insulation, how does that affect it? It's really the same story. Although the rise time in farm oil windings, especially the higher voltage ones, tends to be longer because remember I said we have cascaded stages, and therefore the rise times, at least the ones we've measured so far on machines 3 kV and above, tend to be above about 300, longer than about 300 nanoseconds. So we don't get quite the non-uniform voltage distribution that we can get in, say, in an electric vehicle application. Okay, but the thing that really saves us is the fact that for decades, many decades now, we've used something called mica paper as a turn insulation in higher voltage motors, even on in 50 or 60 hertz applications, but certainly in inverter applications. And that mica is there, even if PD is there, because the presence of mica being very, very discharge resistant, that mica will prevent the rapid deterioration of the insulation. And so we can, in fact, last quite a long period of time, maybe even decades, with PD of at least moderate amplitudes occurring within the turn insulation. So this makes it a much less critical problem. How we make those, apply that mica paper turn insulation, that technology has been around for decades. So it was a fairly easy thing to do. But if the voids are too big and the discharge is too big, then as we'll see, we can get failure. So here's an example of a motor in a steel mill. Here you can see the copper conductors. This isn't the actual coil that failed. This one is from the same machine. But here's the epoxy mica ground wall insulation. I haven't talked about that too much, but you see these black marks in here. That's actually voids where, unfortunately, the manufacturer didn't impregnate it well enough. We get large voids here, and because of this uneven voltage distribution, you get partial discharges occurring here, and given time, even mica or mica paper will eventually puncture and you'll get a turn-to-turn short. And as I said much earlier in this presentation, a turn-to-turn short gives rise to high circulating currents and melting copper, which is what I'm trying to show here. Okay, so these things do happen, but it's, you know, impregnation with voids like this, as gross as this, it's not too likely these days. Older machines, it was quite common, but nowadays modern manufacturing tends to make these things rather small if that process is under control. Thermal aging and ground wall PD, I'm going to skip over in the interest of time. But the last thing I really want to focus in on is the effect of the voltage impulses from the drives on the PD suppression coatings, okay, that are on the surface of the coil to prevent PD, phase to ground PD during normal operation. Okay, and it turns out when we have these very high frequency components, you know, megahertz components hitting specifically the silicon carbide coatings, but even the semicon coatings, current really doesn't want to flow through those coatings because they have a relatively high resistance unless they've been purposefully designed for this application. So it really is, again, focusing on the capacitive currents that flow at a megahertz as opposed to what happens at 50 or 60 hertz. Okay, so let me skip the words and go directly to a diagram. Here we're looking at this sketch from the rotor. Here is the stator core. This is a coil that's coming out of the stator slot. And this skinny little stuff here, which is actually quite fat usually, is the copper conductors. But I'm an insulation engineer, so I like focusing on the insulation. So the insulation is nice and thick here. And under normal 50, 60 hertz conditions, what happens is there's a capacitance between the copper and this magic silicon carbide coating, the ECP. Okay, and how much capacitive current that flows through this transmission line type model of the silicon carbide area is depends on the voltage that's across each capacitor and the frequency of that of the AC. And in normal 50, 60 hertz applications, they designed the particles and the particle density and the particle shapes of the silicon carbide so that this resistance is really, really high to 60 hertz if you have at this end. And as you get closer and closer to the semicon here, the slot coating, the resistance gets very, very low. Instead of being hundreds of kiloohms or megohms, it comes down to almost tens or hundreds of ohms. And the idea here is by the capacitive currents flowing up through here, that the currents will flow through that resistance, and these resistance will self-adjust to make sure we have a linear voltage drop across each of these 5 resistors. Okay, so that's how it's supposed to work. But what happens when we go from 50 hertz up to 1 megahertz? Well, now you've got 100,000 times more current or higher frequency, and you're going to be pushing a lot more current through there. And in fact, the current doesn't want to go through that high resistance path in that silicon carbide. What we found is the current, in fact, is basically is capacitively shunted directly to the silicon, to the semicon layer, which might be a few hundred or a few thousand ohms per square, and then we get a lot of heating here. Okay, so you have a huge current then flowing right directly here. Remember, path. The current doesn't want to go through a high impedance path. It goes through the lowest impedance path, and it creates a lot of heating here. And that can add up to 40 or 50 degrees, unless it was designed for it, 40 or 50 degrees to that temperature there due to I²R losses. And the net result of that is that temperature rise on top of the normal operating temperature of the motor means you can easily get well into the 150, 200 degrees C range pretty quickly. And essentially, the semiconductive coating and the silicon carbide coatings will just disappear. Okay, and you get due to this high overheating, and that will then give rise to very high levels of discharges, and those discharges will eventually then lead to a ground fault. So it's really caused by the fact that the capacitive currents, when you're dealing with much higher frequencies of voltage coming from these drives, is going to cause a lot of extra heating of especially the semicon coating. And in fact, that's where the heating occurs, is at the armor. So this is a nice old picture that was taken at the University of Waterloo. There's the stator core here, the coil coming out of the slot. And this is the semicon tape here, and this is the silicon carbide tape here. And what happens is there's normally a little bit of heating here, maybe a few degrees from the I²R losses of through that junction of those two materials. But when you're under pulse load, okay, and unfortunately the temperatures aren't indicated here, but this can be 50 degrees warmer than normal. So this is where the current doesn't even tend to go through the silicon carbide material. It just gets shunted directly to the semicon adjacent to the end of the core. Now, there's some very nice models that have been produced on this, finite element models that have been produced on this to duplicate this. This is just some pictures that ABB took a number of years ago of the same thing. So it turns out, of at least in my experience, looking at a lot of machines that have failed, and I tend to be a person who looks at things like that, that's where I get my jollies, is that we find the problems are really with the stress control coatings if it has not been purposefully designed for this. So you really can't retrofit a voltage source PWM drive to a high voltage motor. That's just suicide for that motor, in spite of some possible commercial claims that are out there. And sometimes we also see turn insulation issues if there's been poor impregnation of those coils. Okay, and I see I'm pretty much at the end of time, so I'm just going to, this will be my essentially my last slide. Their industry, first with the random wound machines, and then secondly with the form wound machines, the motor manufacturers realized they had to do something to address these issues because they could result in premature failure fairly quickly if conventionally designed machines were connected to these converters. And so we ended up developing two different kinds of standards. One was basically for what we call type 1 insulation systems, where the insulation, the entire insulation system, is purely organic. Okay, this normally means random wound machines, but might not always be that. Okay, so where PD is if it occurs, is going to cause rapid deterioration of the insulation, which is what's going to happen if you have purely organic materials. Then we created IEC 60034-18-41, and basically what it's saying is you have to make those windings partial discharge free at the expected, plus a safety factor, impulse voltage that you might see on that machine terminals. So that's what that comes down to, is the machines have to be partial discharge free at a voltage, at the maximum voltage you expect that winding ever to see. Okay, and so how do you know what that voltage is? You either have to calculate it or you have to measure it. Okay, but we're looking for it to be PD free, just like for power cables and transformers and switchgear, which also are primarily use organic insulation, and they have to be PD free at some type of overvoltage. However, because we use mica, okay, and mica is extremely PD resistant, and virtually every machine that's ever been built rated 3 kV and above has at least some level of PD, and they can still last 100 years. We created a separate standard, IEC 60034-18-42. It's mainly for form wound windings, but it's really for windings that contain insulation that's PD resistant. We're calling that type 2 insulation, and here what we do is we apply, we require the insulation components, the turn, the ground, the phase insulation, the stress relief coatings, to be able to withstand voltage impulses that are expected to hit that machine for the expected life of that machine, whether that be 20 years or 30 years or 50 years. So what we have is a whole series of voltage endurance tests. The windings do not have to be PD free. We in fact expect PD. We just have to show that it can withstand the partial discharge stress. So I've got a bunch more slides telling about this in detail. But I think it's time to come to the conclusion and basically say, hey, if you have short rise time, high voltage switching impulses from PWM voltage source inverters, it will create some new aging mechanisms for stator windings and rotor windings if it's a doubly fed induction generator, that more than the normal aging mechanisms that would always occur anyway, the normal thermal, thermomechanical and mechanical and contamination related aging failure processes. There have been solutions for creating PD-free machines for type 1 windings, and they're pretty much available from all the motor OEMs, although they are supposed to prove that they can be made, those windings are PD-free at a specific impulse voltage plus a safety factor. And in the case of the form-wound windings, the issues have been turn insulation, but more importantly, the stress relief coating insulation problem. I think there's still some way to go on solving all the stress relief coating issues that can have in millivolt stators in medium voltage machines, especially as the rise times are going to get slower, shorter and shorter. And so I think there's still work to be done, but at least we do know motors now, at least I'm aware that motors can be made for this converter application and be reliable. Okay, that said, Mateos, I think I should stop.
Yeah, thanks, Greg. This is very interesting and very informative presentation. Yeah, thanks. I think with increasing renewables integrating to the grid, we're gonna see more high frequency, especially with IGBTs that has very fast turn on time, less than 100 nanosecond. So the email address of Dr. Greg is here, g.stone@ieee.org. You can have any follow-up question email to him, but I will just select a couple of questions from the Zoom chat, and maybe Greg, you can address some of them. The first question is from Okumu. Can the effect of inverters in PV plants affect the transformers in a way similar to motors and generators?
Yeah, the short answer to that is yes, especially they tend to be dry type transformers. And so in many ways, they do look like machines. This is not my specialty, but I am aware there have been issues. So again, there's the non-uniform voltage distribution through the windings of a transformer, and therefore you can have PD activity where you would not normally expect it to occur.
All right. Another question from Jeannie. You mentioned the importance of eliminating the size of air voids between the turn insulation wires.
Yeah.
Is it possible to completely eliminate all the voids?
In my opinion, no. There's other people who may or may not disagree who might be listening, but I think you're always going to have some level of voids with the manufacturing techniques that we're using now, which is basically various kinds of impregnation. And what I've seen, and of course this is just what I've seen, is that in the early days, a lot of especially the lower voltage motors, they just use what's called a dip and a bake process, where they dip the whole stator in a tank of warm varnish, and they hope that it would impregnate it, and then they put it in an oven to cure it in place. But the reality is it doesn't get rid of all the voids. Then people then started moving, when we started seeing these issues in the late 80s, early 90s on the random wound machines, they moved to a trickle impregnation process, combined maybe with a UV curing mechanism and some other exotic chemicals and stuff that might that allows better impregnation. But I think to make sure you have the minimum possible voids, you really need to be moving for inverter duty motors. You really need to be moving to a global vacuum pressure impregnation, where you suck a vacuum, you put it in a tank, you suck a vacuum, you introduce a resin that will cure, and maybe there's some accelerators and stuff going on in there, but by trial and error, you get the right amount of time to allow the epoxy to penetrate there and starting to solidify, and then of course and push that resin in under a pressure, so that you fill those voids. That's vacuum pressure, and then you apply heat to cure it. Okay, and at least in my experience, most people have been able to. I haven't talked about partial discharge inception voltages, or more correctly, repetitive partial discharge inception voltage. But generally speaking, if you switch from, say, the dip and bake method, which most conventional motors or low voltage motors are made with, to the global VPI process, you can easily double the discharge inception voltage, but you'll never get rid of all the voids. Okay.
All right. Yeah. Maybe last question from Deep Park in ABB. What is the effective way of measuring PD in random wound stators? I know this could be a long
Yeah,
discussion,
that's
but
you know, that's a subject I chose not to talk about here, just because it's one of those specialized subjects that you can go on and on and on. What you can't do is use a conventional IEC 60270 PD detector to detect the PD, at least the PD that could occur between turns. Okay, you can use a conventional PD detector, which work in the, you know, the 10 kilohertz to 1 megahertz region, IEC 60270 standard. Okay, you can use that for detecting problems in the ground and the phase insulation. And in IEC 60034-18-41, we did make provisions for that. But if you're going to test the turn insulation, and if it is a fully manufactured conventional motor, stator winding, you really have to apply impulses, okay? But those impulses, the device that creates those impulses creates a lot of transients that are literally 1,000 times bigger than the PD you're trying to look at. And so what we then do is move to very high frequencies. There was the company I used to work with, they made a specific device that measured the actual current pulses that could distinguish the PD from the stator winding from the impulse coming from the converter, but that turned out to be a bit expensive. Now what people are doing is the antennas. Basically, you're using hundreds of megahertz antenna or even a gigahertz microwave horn antenna. That you apply at the same time you're applying the surges from an impulse tester. With the right rise times, and those and because you're at a very, very high frequency compared to the 100 nanosecond rise time, the issue becomes you can just basically separate it in frequency, but because it's an antenna, it depends on where the PDs are current, whether you're going to measure it or not. And as we move to the wideband gap type inverters, so the silicon carbide type switches, where the rise times are in the 10 nanosecond range, that's the same rise time as the PD. Okay, and using the frequency method is a lot more issue. So there is research still to be done in that area. Okay, but you know, the impulse testing manufacturers, and there's several of them out there. Most of them now are giving you a little antenna, which is just a little patch antenna. It's a very simple device. Normally it's just some coax cable with the shield removed and potted, so you don't know that's all it is. And but where you position that can affect sensitivity, and that creates a bit of a problem. Okay, and so that's the issue going forward.
Okay, understood. All right. So I think that concludes our webinar. Before I close today's session, let me share my screen and give you a little bit on next month's webinar. As I said before, we are hosting this webinar monthly, and our next webinar will be on May 9, and the speaker is Dr. Lionel de Villard from Keptos. He's the chairman and CEO of Keptos, and we will be talking about electric field purpose for research and industry. We will send e-notice and advertise in our LinkedIn. With that, I will close today's webinar. Thanks again, Dr. Greg Stone. Very informative. I know today we were at our maximum Zoom capacity. We had 100 participants, and I just got email that many people cannot join. So we already recorded this one, and we will be sharing it at DEIS website under educational video. Okay. All right.
Thank you very much. See you, folks.
All right. Bye-bye.